good morning everyone. I'm going to present chapter 5 phase equilibria. So for phase equilibria, for the first one is phase diagram. So what is phase diagram is equilibrium phases are at various temperature, composite and pressure in graphenic representations. So in phase is a region in the system in which the properties and composites are spatially uniform. So for phase 2 is phase diagram are equilibrium diagram and condition for equilibrium phase constraint on the degree of freedom F. So that's a system process Gibbs. So for the formula is F equal to C plus 2 minus P. So F is degree of freedoms and C is the components and the P is phase present and the 2 is external variable temperature and pressure. So to identity of phase is by analysis is XRD patterns. So for liquid is number of phase is limited, it is a single phase, so it may be alcohol or it may be water. And for gases is only in one phase. So the numbers of components, the minimum number of constituents needed to fulfill the description, the components of all the phase present. So for one component system, when we put is in C equal to 1, so when we sub into inside, then we will get a degree of freedom is 2. So F equal to 1 plus 2 minus the one component system, so is 1, so it will be equal to. So for in the phase diagram, the pressure is 2, then it will be F will be equal to 1. So for at 1 atm pressure, the water and ice can exist at only one temperature, which is 0 degrees Celsius. At triple point, 3 phases coexist is degree of freedom will be equal to 0. So the 3 phase must coexist at unit temperature and pressure. So for single phase substance are heated or coolant that can undergo numbers of polymorphic transformations, which is dysplaxive and reconstructive. Okay, so for the reconstructive transformation and dysplaxive transformations, for the reconstructive transformation is involve a breaking of and rearrange of the bonds. So the transformation usually occur in nucleations and growth. And displacive transformation it doesn't involve a breaking bonds and is occurred by displacement of atomic lengths relative to one another. So what we can see in the diagram is like you can see the reconstructive transformation will be the changing of the arrangements and the bonds. And for the displacive transformation is only it doesn't breaking the bond, but it's also changing the shape. And then for the example is zirconia. Is upon heating under 1 atm, Zr goes through the following transformation. It will be from monoclinic to tetragonals to cubics and to liquid. So it's exhibits 3 wells deformed of polyforms. It's monoclinic, tetragonals and cubics. And another example is barium titanate, and its heating, it will be from a robohedral to orthohorbic tetragonals and go to the cubics. And it will have a distorted periodic structure. Okay, so for binary system, it consists of 2 components and influenced by 3 variables, which is temperature, pressure, and components. So its most ceramic binary are exhibited in the partially solubility. So for 2 components are mixed together and allowed to equilibrate, 3 outcomes are possible. So for first is mutual solubility and solid solution formations over the entire composite range. It's known as complete solid solubility. And second is partial solid solubility without the formations of an intermediate phase. And the last is the partial solid solubility with the formations of intermediate.
So today I would like to explain about the solid solution. So there are 2 ways for solid solution to happen, which is first substitutional and interstitial. So firstly, I would like to explain about substitutional. Substitutional is solid ion which is directly substitute for into the host ion nearest to the electronegativity. Macam kita belajar waktu awal dulu, substitute dia ganti kan. So in substitutional, the cation will substitute with cation and anion will substitute with the anion. So for example, the host is NiO, the substitute is MgO. So Mg for the ion is Mg2 plus. So it will substitute with Ni and O minus with the anion. So it will produce a solid solution of Ni1 minus X MgXO. Okay, so next is interstitial solid solution. So for interstitial, the solid atom is small, which it dissolves interstitially into the host. So before, like we learned before, interstitial, the small atom will try to penetrate into the vacancy of the closed packed atom. So for interstitial to occur, it depends on the size of interstitial site on the host lattice, which relative to that solid ion. So for example, I take rock salt. Rock salt, it have a very close packed structure. So interstitial solid solubility is very not likely to occur since it has a very close pack. So very quite difficult for the small atom to penetrate into the vacancy. Next is fluoride. Fluoride, it has a quite large size of interstitial, so it makes the interstitial solution to form easily for this structure. Okay, so for the next part, I will explain about the complete solid solubility. So there are a few factors that will contribute to the complete solid solubility. So I will explain two from the part, which is first the structure type, and next is the valency factor. So for the structure type, the two N members must have the same structure type of solid. Two N members must have same structure type. So for example, I will take as SiO2, silicon dioxide, and titanium dioxide. So silicon dioxide and titanium dioxide, they are not expected to form a complete solubility since they have a different structure type. So next, moving to my next point is valency factor. So for valency factor, the two N members must have the same valence. So if the members does not have the same valence, so if it does not have same valence, what will happen? So if it does not have the same valence, compensating effect from the host crystal might occur, which this effect is to maintain the charge neutrality of the substance, of the material. So the greater the difference valence, greater difference valence. So the lower the stability. The lower the solubility. So these two are part of complete solid solubility. So I will pass the next to my partner. Thank you.
to continue from my friend's part. I still talking about complete solid solubility. For to get a complete solid solubility, there is another factors that we should consider about, which is size factor. For the size factor of the two solvent, we should we have to have less strain energy, because if we have more strain energy, it mismatch the size of solvent and solid ions. So we must have less strain energy to achieve complete solid solubility. Okay. So for that, the size difference between the two between the solvent and solid ions cannot be more than 50%. It should be less than, size difference must be less than 50%. The size difference between solvent and solid ions. Okay. We go to the next factor that affects the complete solid solubility is the chemical effect. For the chemical effect, two end members of that involved in the solid solution cannot have too high chemical affinity. Their chemical affinity cannot be too high. It should be in a smaller or intermediate amount only. If it is have a high chemical affinity, what will happen? The free energy of the system will be lowered by formation of an intermediate compound. It will form an intermediate compound. Okay, next we will see what is the formation of the intermediate compound. Okay, this is an example of a complete solubility where the mixture of nickel oxide and magnesium oxide, you can see is a phase diagram. Nickel oxide and magnesium oxide basically have a lot of structure and application. It is very similar, so they can form a complete solubility. When we look at the 60% composition of 60% mole percentage, nickel oxide is cooled from melting and going down. You can see at temperature T equals 1, yeah. Solid solution of magnesium and nickel oxide will start solidifying. From liquid they will start to become solid. And T equals 2 is about 2500 degrees Celsius. Two phase will be coexist, which is solid solution of composition Z and liquid solution of composition X. They will be coexist at T equals to 2. When T is becoming lower and lower, the composition of solid solution will move along the solidus liquidus line. This is the liquidus line, where it becomes temperature level will move become this side until it form a complete solid solution. At about 2000 degrees Celsius, the final liquid solution and the composite solution will be formed, and the composition of this solid solution is same as the initial composition, which means it is 100% nickel oxide. Okay, tadi ketemuan kita tahu, kita tengok complete factors that affect complete solid solubility. Now, one of the conditions, as we know, for the existence of the white solid solution, domain is the absence of a strong affinity of the end members for one another. But in many cases, in actual fact, many cases, the two members will react and intermediate compound will be formed. Here, the intermediate compound can be melted in two ways. One is congruently melting, another one is incongruently melting. The difference between congruently melting and incongruently melting. Okay, for congruently melting intermediate phase, there will be no change in composition of the two solid solutions that involved. There will be only phase diagram that will be simply split into series of smaller symplectic system. Means it will be no change, just will be remain as the same composition, but just simply split into series of smaller symplectic systems. But when we see for incongruently melting intermediate phase, the thing is the intermediate compound will be different, because it will dissociate before melting into liquid and another solid. From solid compound, it will become one other compound berlainan with liquid. That is the main difference. Congruent limiting means they will not change composition, but incongruent limiting intermediate phase, there will be change where from one compound will become one liquid composition and another solid composition.
Okay, what is a ternary system? Ternary system is related phase, which is in this triangle, it has temperature in a 3 component. Beside that, it also have 4 variables, which is the first one is temperature. The second one is pressure, and the third one is 2 components of concentration. Okay, macam mana kita nak tengok dia punya triangle ni? So kita akan tahu dia ada 3 point, point A, point B dengan point C. Okay, daripada point A ke point B, dia 100%. So, dia akan start sini pukul 0, lepas tu 10%, sini tengah 50 sampai dah sekali 100%. So, sini ke sini pun 100%. Dan C ke A pun 100%. Lepas tu, titik tengah ni kita panggil dia sebagai point. Okay, what is point? Point ni ialah intersection of the boundary curve represent phase in equilibrium. Maksudnya dia represent 3 solid phase and a liquid. Sebab dalam triangle ni dia ada 3 solid phase and a liquid. Okay, so this one pula ialah boundary curve. Boundary curve ni represent equilibrium between 2 solid and liquid. So, senang je nak ingat dia, sini kita punya intersection sebab dia antara 3 ni dia bertemu, dan ni dia pun yang garis ni pula dia punya boundary curve. So kita tahu yang ni pula, yang point ni, the lowest temperature at which liquid can exist as a ternary eutetic. Contoh, macam kita cakap tadi, A ke B 100, B ke C 100, C ke A pun 100. So macam ni kita nak kira. Okay, contoh, dia punya point Y ni dekat sini. Okay, point Y. Kita tahu kalau kita cari tu, kita punya point tu kena sentiasa perpendicular on each other. So contoh, kita punya sini, kat sini, so sini 50%. So kita tahu A, B kita 50. So kita kat sini. Sebab perpendicular kan. So B ke C dia 19. So kalau yang ni pula C ke A dia 18. So macam ni je. Mol AB, mol BC, mol CE. So kita tahu macam tu. Okay, sama juga kalau kita letak point ni kat mana-mana pun. Contoh point ni kat sini, yang ni X. So sama juga dia kat mana. Kalau kita buat yang clockwise, so kita kena ikut clockwise je. Kalau kita buat anti-clockwise, kita ikut anti-clockwise je. Sama je macam ni, macam ni. So dia punya nanti sini, dengan nanti sini. Okay, macam tu. Okay, dalam ternary system pula, dia ada isothermal station. Isothermal tu ialah perubahan is a change of a system in which the temperature remain constant. This occur when a system in a contact within outside thermal reservoir and change in system will occur slowly enough. So kita tahu isothermal process ni dia punya perubahan is perubahan tekanan over masa.
Equilibrium state the phase or combination of the phase for which the free energy is at the lowest. For the first one is polymorphic transformation in unary system. First of all, what is polymorphic transformation? Polymorphic transformation is change in atomic structure of mineral, but not involve change in chemical. So, it occurs in congruent melting of a compound. What is congruent melting? Congruent melting occurs during the melting of a compound where the composition of liquid that form is same as the composition of the solid. The T depends on the free energy function. Can be seen liquid. The free energy equal to enthalpy of liquid minus entropy of liquid, which is H is enthalpy and S entropy. For solid, the free energy function is equal to enthalpy of the solid minus entropy. Free energy changes as T is lowered below the equilibrium temperature, Tm. So, refer to this graph, you can see that at the point of intersection is the melting point, Tm. Liquid will not exist below Tm, but liquid will only exist above Tm, which is the melting point. At this point, which is known as T, the free energy at T is below from the melting point, Tm. So, approximately it as same as the heat fusion, which is T minus Tm over Tm, melting point. Assuming they are linear function of T, which is only valid if the heat capacities are not strong function of T and the T range considered is not too large. The free energy of liquid is steeper than the G of the solid. It is because the entropy constraint of liquid is larger, which is more disordered, than solid. That's why it becomes steeper. At the point T above the melting point, T above melting point, the line intersects and the liquid has lower energy enters is more stable space. So now I will explain about complete solid solution. For free energy versus composition, diagram for AO, BO mixture exhibit complete solid solubility at temperature that is lower than solidus 9. So this point is free energy of AO, and this point is free energy for complete solution AO and BO. Free energy versus free energy versus composition diagram for a system that exhibit completely solid solution, which is consists of two vertical axes that represent AO, pure AO, and pure BO. M not AO is the molar free energy of formation, which is in free energy form, G form, of AO from its element. And this one, M not BO, is the molar free energy of formation, which is G form of BO from each element. So, in this graph, AO has lower free energy than BO. So, the solution is assumed to be ideal. That is, Hameed heat of mix is equal to 0. Thank you. So, I will pass the equation of free energy of mixing of AO and BO to Sofia. Thank you.
And I will continue with the equation of free energy of mixing. Yes, free of energy of mixing is the mole fraction of AO multiplied by the molar free energy of AO plus mole fraction of BO multiplied by molar free energy of formation of BO minus temperature multiplied by entropy of mixing. Okay. This is equation 1. And for the entropy of mixing is equal to constant temperature molar free energy of formation of AO ln molar free energy of XAO plus molar free energy of BO ln molar free energy of BO. Okay, this is equation number 2. Okay, if we combine these two equations, we will plot the graph of G-mix and the composition, and the curve it will be curve like this, which we can determine the free energy as composition function for the liquid solution. Okay, the combination of these two equations also will make the graph dissipate like this, like T1 graph and T3 graph. As you can see, this is a several type of graph that show the graph of temperature versus composition versus free energy. Okay, as you can see, at T1, the liquid solution show the lowest free energy. At T3, the solid solution show the lowest free energy composition. And as for T2, at the point at here, it shows that the liquid solid solution have the lowest free energy state. At here, show the solid solution have the lowest free energy state, which is more stable state. And if there is interaction here, so at the point it will show the lowest free energy of the both system. Lowest free energy of the both system will occur only if there is intersection between liquid solid solution and solid solution. This graph is a stoichiometric and non-stoichiometric composition graph. Okay, as we can see, this is this line represent the stoichiometric compound. This is a graph that represents the stoichiometric and non-stoichiometric component. This line shows the stoichiometric component, which is it only exists over a very narrow condition. And this is a non-stoichiometric compound. It will assume that the non-stoichiometric compound only exists between the stoichiometric. So it usually here in the middle of the stoichiometric line. Okay. So the non-stoichiometric graph line show the lowest energy state, and there is a range of stability because there is a gap between here and here. So the